My name is Frank Rosenzweig, and I'm the director of the University of Montana Institute on Ecosystems, and it is my great pleasure and privilege this evening to introduce to you my friend Tim Lyons. Tim Lyons is a distinguished professor of biogeochemistry at the University of California, Riverside. He is the recipient of many honors, a few of which are that he's a fellow of American Association for the Advancement of Science, American Geophysical Union, and other societies. He publishes extensively in the field of biogeochemistry, and at the University of California, Riverside, where he's been for the last 20 years, he leads the astrobiology program, and a program that continues to focus on a theme that really he pioneered of what he will describe to you as alternative Earths. So this is going to be a theme of tonight's lecture. And so, you know, what does this phrase alternative Earths mean? And why should NASA be interested in it? And why should you be interested in it, just as, you know, John Q. Public interested in science? Well, what it really means is that this planet of ours has been inhabited for most of its 4.5 billion year history. In fact, the most recent data that were published this past summer in Nature by Moody et al. Suggests that the last universal common ancestor can be dated back to 4.2 billion years old. And because this organism, this hypothetical organism, had a large genome and sophisticated metabolism, it suggests that the origin of life occurred much earlier than that. What it means then is that for more than 95% of Earth's history, Earth has been inhabited. And over that time, Earth and life have co-evolved with one another. And so Earth has been in many different states, so that if you were an observer from another planet, distant from ours by light years, and were looking at Earth through your favorite telescope, you would have seen over that 4.5 billion years a very different planet. And so tonight, Tim is going to tell you how he and his collaborators over the years have used the rock record chiefly, and the ratio of isotopes in the rock record to make inferences about Earth life coevolution over most of the Earth's history. And that's...
Well, thank you, Frank. It's almost like you heard me just speak on this to provide that summary. That was amazing. Let me see if I can get this mic better. How are we doing? That's okay? Okay. Well, thank you all for coming out on a cold midweek night. And thank you, Frank. You know, I'll spare you the details, but Frank and I have gotten to know each other well over the past 10 years, and it's been really one of the highlights of my increasing NASA connection, and that Frank and my world have converged in the ways that they have. And so that was very kind, and it's wonderful to be here. I have done a lot of different things, as many people in academic positions have, and what I want to do tonight is give you really sort of a little bit of a journey through how I got to where I am and what I do, but also, you know, start in a very grassroots kind of way, like what it's a little bit of a family, or Tim Lyons, this is your life. And, and I think the lesson in that is that, you know, as I said to people today, you just never know where or how you're going to end up in a place that can be quite remarkable. And so the work that I do now, I never could have predicted even when I was leaving my PhD. And so you keep your eyes open, you use your gut instincts, grab at opportunities. And so now Frank and I and others are so deeply embedded as non-planetary scientists, non-astronomers. I will confess something tonight that I used to be embarrassed to connect. I've never had an astronomy class. And I've also, this is really embarrassing, but I think I've compensated well. I have not had a biology class since 9th grade. So what it means is that we're lifelong learners, and that's why some of you are here tonight, right? It's like I am constantly given opportunities, and it keeps us going, right? It makes retirement nearly impossible because every day there's something new around the corner. I'm doing a lot of climate change work now, and it's just, I'm as excited about that as all the things I've done through my life, and it's just, I feel very fortunate. And with the people that I've worked with, and with the science that I've done. And I would note in particular the research group that I've had, my postdocs and PhD students. I've had somewhere between 50 and 60 postdoc students, and they're almost all doing extraordinarily well in places that are remarkable. And so it's an academic family, and so it's common in our fields now to have these academic family trees where you can see all the different branches. And I'm meeting my academic grandchildren and even great-grandchildren, and it's I think that's what lives on, right? That's really what our legacies will be. My oxygen curve, maybe it'll be obsolete in 10 years, but the generations of people well, the people that we've spawned, and well, there'll still be oxygen. But the generations that we've spawned and that are spawned by those people are quite a happy part of the world. So I'm going to really address two fundamental questions tonight. Are we alone? And how did it start? And so, what do we know about the beginnings of life? And, we live in interesting times politically and otherwise, and I think that that we forget that we are still, at our core, curious human beings, right? And we can wake up every day and not necessarily just have to worry about the headlines or worry about whether the car is going to start, but we can also still ask these great questions that ultimately drive us. There's a question of living, but then the bigger question is why we want to live. And I think those motivations for why we want to be who we are and where we are often lie in these kinds of things. And so I'm gonna highlight those things, and I'm gonna give you a little bit of baseline of how I got to these places. I was fortunate, as was Frank, to have lived through the entire glory initial period of the space age. So I have stamps from every Gemini and Apollo and Mercury launch. I can remember well 1969 in July when there were the first steps on the moon. I can remember the TVs in the back of my classroom where we would get to take a break during the middle of the day and watch a launch or watch a splashdown or watch steps. And it would be impossible to not be influenced by all of that. So these are really the images of my childhood. And I lived near New York City. I grew up in New Jersey, and so I remember the ticker tape parades when the astronauts would come back. And I mean, these were true heroes, and there was no political discussion about it, right? It was, the mission was launched by Kennedy in the very early 60s, making this commitment to, I think at a lecture in Texas, maybe Texas A&M, making this commitment to putting a man in that case, on the moon by the end of the decade. And there was a huge financial investment, and there was an extraordinary technological advancement in the age where we had nothing like the computational powers that we have now. And so it's one of the great feats, I think, in the history of humankind. And so we are faced now with similar opportunities, the idea of maybe finding signs of life around planets that are light years away, around other stars, and exciting research on Mars, and ripped from the headlines are exciting opportunities that are being pursued for the icy moons that are around some of the planets within our solar system. So I'm going to talk about some of these things a little bit. And so here are, again, just ripped from my memories. And I also, I graduated this year from high school when the first spacecraft landed successfully, the Viking mission landed successfully on Mars. And so that was pitched as the earliest effort to try and find life in situ by landing on Mars. It did not do as promised, but it certainly put an awful lot of things in motion that are with us today. And so I have increasingly been doing Mars work. I'm close enough to Mars that I get asked to do a lot of things because I don't have conflicts. It's a big community and they all work together. The papers often have like 50 authors on them, so it's hard to find someone who can lead a senior review of a program or do those sorts of things. So as I said recently, I dance on the margins of Mars, and I often will put my foot in. And I've had students and postdocs working on Mars. And as you all know, the Perseverance rover is there now, and there's the exciting possibility of having sample return, and Curiosity is still going strong. I'm involved with the senior review of that. I can say that. It's ongoing right now, and Curiosity has started to move up Mount Sharp into the sulfate zone. And so we have captured fundamentally the transition from a wet lake sequence into Mars starting to dry. And so there are basic questions about why Mars was wet and how climate changed and what drove those climate changes, and whether there was life that was living in the water that was present on Mars those 3.5+ billion years ago. And so we see lots and lots and lots of evidence for Mars, for water on Mars in its past. And so here we can see deltaic sediments and a crater that's on top of that. This was a long time ago that this water was here. And this just blows me away. It might as well be Death Valley, right? But this are lake sediments in the middle of the Gale crater where Curiosity is right now. And so it's really hard to imagine that this is so far away, and I feel like I could put my boots on and walk across it. So these images come out all the time, and here is Curiosity that is still going strong. The review that I'm involved with now is for what's called the 5th extended mission. Every 2 years it goes through an evaluation, and they give them the big chunk of like $40 million a year to keep going on. And so it is going far longer than anticipated. The wheels are starting to degrade. Instruments are starting to lose their power sources, but it still keeps going like the ever-ready bunny, just keeps ticking on. And so the data keep coming back, and there have been remarkable discoveries. And I would say that what the Curiosity mission is best known for is really proving and detailing the past history of a wet Mars. All right? So if you had any doubt that there was water on Mars, you would no longer have that based on those observations in particular. And so this is what Mars may have looked like 3.5 billion years ago. And it's not easy to explain this water because Mars is that much farther away from the sun, and when the water was there, our sun was perhaps somewhere between 70 and 80% as bright as it is now. So it's out on the outer edge of the habitable zone, as we call it, which is defined by sustained liquid water. And so the climate models that are invoked to explain this still suffer. To imagine what the atmosphere was like and the greenhouse gases that were required to keep this cold world, even colder than today, keep it within that narrow temperature range that supported oceans. So the best guess now is that it was carbon dioxide, but that's still a guess, and that the water was probably transient, that it would come and go. But it was there enough to affect the surface of Mars, the geomorphology, and it was enough potentially to have generated and supported life. And so we also have orbiters that have many functions. One is that they can broadly survey the landscape, and they can tie into rover observations. So an orbiter sees something and it thinks it might be a particular rock type, and if it's in an area where there is a rover, they can test to see whether that assumption is right. The orbiters, are also used to relay data from the rovers so that when instruments are downloading their information, it can be relayed to an orbiter and then sent back to the Earth. So there's a constant data dump that's coming from the myriad instruments that are on both Curiosity and Perseverance. And this is what the Perseverance rover looks like. These are sort of on the scale of minivans. If you've ever been to JPL, there's a test bed there that has another rover. So if they have to do any testing to see what can we do to fix the wheels on a fly or whatever, they have one of those. So I've stood next to it, and they're not huge, but they are workhorses, as Curiosity has demonstrated. And before that, Spirit and Opportunity that went far beyond what people imagined. And so what this is doing is it has multiple instruments that allow them to do at least fairly sophisticated geochemical analyses in situ on the Mars surface, but also it's drilling samples. And many of you will know that what the Perseverance rover is best known for is the goal of drilling samples and returning them to Earth, right? So we've been hearing a lot about that. It will be the first thing of that sort, other than the OREX mission that returned material from an asteroid, and we've sampled from cometary tails. But to be able to return samples from Mars is an important step in the idea of putting humans on Mars and bringing them back, but also having these incredibly fresh, pristine, carefully selected samples that have been analyzed in situ for their context, but then brought back to instruments that can do extraordinary things in labs like here and other universities and NASA facilities. And so there are different strategies for what the sample return might look like, and you've been hearing this, and I would say stay tuned, because the budget is up to something like $10 billion right now, and it's just a few dozen samples that are about the size of a cigar. And so you can say to yourself, that's a lot of money, especially given things that are also requiring great sources of money. I work in the Salton Sea in California, which is a great environmental problem. To fix that might be something like $10 billion as well. These are large numbers by any measure. And so the JPL design has gone with, well, the cost estimates keep increasing, and the delays have been significant enough that they've now taken this plan and thrown it back out to the community to come up with new ideas. It may still end up with JPL, but it's not clear exactly how it's going to be done. But almost certainly any model that's chosen will involve the idea of collecting samples that are stashed on the rover itself. There are also samples that were laid down on the ground surface, but almost certainly that it'll emphasize the samples that are on the rover, and one way or another, perhaps by a separate collection rover that will go over to Perseverance and pick them up. They'll be put in this space, and it'll be something like the size of a basketball, not very large, and then it will be launched into space where it will rendezvous with an orbiter, which will then come back to Earth. So it's not possible, given the gravitational field of Mars, to have something big enough and powerful enough, a rocket that would be enough to get this off the Mars surface and bring it all the way back to Earth. So it's this kind of handoff to something that is already in space and can then leave the Mars orbit and bring the samples back. So amazing, and every day I'm hearing and reading new things as somebody, again, who's dancing on the margins and sticking a foot in every once in a while. And so there is certainly this idea that a number of prominent people believe that accept that life on Earth, which began, as Frank said, 4+ billion years ago, that could have been seeded through a process called panspermia by transfer from Mars. And so we have Martian meteorites here. It's entirely possible that life originated there and was transferred here, or that life originated here and was transferred to Mars. So we're close enough to Mars that we were in particular early in our history exchanging lots of materials. And so this is something that is a great scientific question. And then you think about what new administrations are doing. There's a lot of interest in this new administration on Mars, and it doesn't hurt that Elon Musk and SpaceX are deeply interwoven into the present set of initiatives. And so Donald Trump promises to put a flag on, promises the moon, and his goal is to put a flag on Mars. He didn't indicate a timeline over which this would be done. Having a human mission to Mars is something that will be in my lifetime, but it's not going to be super soon. Right now, we're focusing on bringing back these samples, and that would be over timescales of something like the next decade or two. But that's remarkable, right, to imagine humans on Mars and returning safely. The other very hot topic right now, and the one that I think, other than exoplanets, that I care most about, are these water worlds, as they're called, or ocean worlds, or icy moons. And there are many moon objects around outer solar system planets. Even Pluto has a fair amount of liquid water below its surface. But the two that you hear most about are Europa, which is a moon around Jupiter, and Enceladus, which is a moon around Saturn. And they both have vast bodies of liquid water beneath an icy cap that is on the order of 10 to 20 kilometers thick, something like that. And the oceans are as deep as many tens of kilometers. So they both have, and Europa in particular, have vastly more liquid water associated with them than the Earth does at its surface. So we have 70% ocean, but the ocean is relatively shallow. These are really deep oceans on smaller bodies, but large amounts of liquid water. Now, these are really far from the sun, and you can say, well, how is it warm enough to have an ocean? And so far beyond our habitable zone, which again is defined by that distance from the sun where you can have liquid water support it over a significant amount of time. The way that this happens is that as these moons go around their gas giant planets, which have solid cores, solid interiors, there's incredible gravitational interaction. And so the stretching and contraction as the moons Europa and Enceladus are going around heat up the rock within the moon interior, generating lots of heat and supporting volcanic activity, high temperature processes within the rocks, and also enough heat to sustain liquid water. And it's only at the outer surface that you have these icy shells that behave a bit like glaciers. They're moving around and they're very dynamic. And so there is every reason to be excited around the possibility for Enceladus in particular. Now, these are plumes of the water that are coming through cracks in the icy shell. And people have found, that missions have found within these plumes hydrogen, organic compounds. Hydrogen is important because it can support life, it can support metabolisms. It's also fundamental in the way that life may have begun. And so you have the right kinds of rock activity on the ocean floor within Enceladus. You have the right kind of materials to sustain life. And so it's really very possible that Enceladus generated life on the seafloor in some ways, that people think that life originated on Earth rather than on land, on a deep ocean floor associated with high temperature fluids coming to the surface. And so it's really possible that we'll fly through this, and the new NASA decadal called for an Enceladus mission on timescales of the next 10 to 20 years. So we will have data with instruments flying through, orbiters with instruments flying through the plume and collecting material and looking for organic and biological materials. And right now, we're excited because in 2024, the Europa Clipper launched, and it's traveling its slow, long path, not so slow, but long travel time to Europa, and this is what it's going to look like. You'll be hearing more and more about this. The radiation field within this inner portion of the Mars orbit, or excuse me, the Jupiter orbit, it's just too extreme to leave the orbiter there. So what's going to happen is that it's going to fly through past Europa, and it's just going to keep doing that. It's going to do these flybys, and it's going to do it enough times over a long enough period of time that it's going to characterize most of the European surface. So we're going to look at that ice, we're going to look at the materials that are present on that ice, and start to conjecture further whether these things could be supporting life, could be evidence for life. And so I love the idea that there are places far beyond our own planet that are supporting liquid water, which is the central, essential ingredient in life. The search for life in other worlds always begins with the idea of past or present water. And so for me, much of the journey began back in the 1990s. And so in 1984, there was a meteorite called Allen Hills, and you'll see a picture of this in a second. I'll give you the full details of that. But it was found in 1984, and this is what it looks like. And it's one of the most famous rocks really ever collected on the Earth's surface, this ALH 84001. It was collected in 84, but in 1996, there were a series of papers that were published in prominent journals that argued that there were multiple lines of evidence for past life on Mars. And that includes these little features that were thought to be microbial cells that were preserved, little microfossils within the sample. There were geochemical arguments, mineralogical arguments that were all sort of lining up in the scientists' minds as signals of life that are found within a rock from Mars that was collected in the Antarctic. The problem is that all of these arguments were quickly challenged, and so there is nothing from the Allen Hills meteorite that would convince very many people these days that there was life on Mars from this sample. And NASA was very excited about this, and they had press conferences, and there was a massive release. The White House was talking about it. It was a really big deal. And so not so much an embarrassment, but a bit of a reality check as these things were challenged, and ultimately the conclusion was that they were not signs of life. And so NASA realized that the challenges to life detection are hard, and it opened up additional doors of opportunity for work that made NASA and us as a community better at arguing convincingly when life is present. And so that included work on Earth samples, these terrestrial analogs. And so what that means is that someone like me, who's trained as a geologist and spends most of his time looking at rocks that span billions of years on our own planet, can develop techniques for life recognition that could be extrapolated, could be extended to work in other places like Mars. And most importantly, what it did in 1998, and Frank and I both benefited from this, it spawned what's called the NASA Astrobiology Institute. So what that did is it brought together large teams that were funded over 5-year periods, broadly integrated in many different disciplines to ask fundamental questions about astrobiology. Astrobiology is that idea of looking for life elsewhere and using the Earth in many respects to try and inform those searches. And so we assembled a team. I was part of Can 1 a long, long time ago, from the very beginning in 1998. And then in Can 7, I led a team with quite a bit of money and wonderful scientists as we tried to develop this idea of better using Earth and that cryptic record of 4 billion plus years of life on Earth to understand better how to look for life elsewhere. And so it is a study of the origin and evolution and distribution of life in the universe. I would say we do live in really interesting times and critical times for astrobiology. Frank could tell you, as I can, that it's going through a lot of change right now. There's a lot of change in leadership, and we have conversations and ask each other where we think it's all heading. But it's not going to go away. It's one of the 5 fundamental goals of NASA. That is to ask the question of, are we alone, and what else can we do that we're not doing already to try and answer that question. And so the levels of investment ramp up. These are big missions that are going to Europa. The rover missions are massive amounts of money, of hundreds of millions and billions of dollars. And so as those investments ramp up, so do the expectations. If you're going to bring samples back from Mars for $10 billion, you should be bringing the right samples back and have some hope that they're going to shed some light that you could not shed otherwise. And so it's stressful on some level, but they're very reasonable expectations if we're going to be supported at those levels that we deliver as promised. And so I think also it's really important to remember that we don't want to define astrobiology as a binary. In other words, if 5 years from now, 10 years from now, 20 years from now, if we haven't found life, that we don't view it as a failure, because in the process, we're learning so much about how to look for life. We're developing technologies that allow us to do it in increasingly sophisticated ways. We're learning more and more how to use the analytical capabilities and observational capabilities here on Earth to do that. And so it is like, when you fly through a plume in Enceladus, whether you see signs for life or not, it's remarkable. The engineering feats are remarkable. And so we have to be strategic as we think about it. We keep looking. And as I said, a lot of it is about messaging, or I've alluded to that while feeding, as we're looking, we feed the collective mind with the many wows that are discovered along the way. And those wows are not only defined by finding life, but they're defined by the search itself. So in many cases, the journey is as exciting as the destination, and that certainly is the case for this astrobiological goal. So in astrobiology at NASA, it's changed through the years. The Astrobiology Institute has been replaced by a number of different things, in particular, this collection of what are called research coordination networks, and Frank is a leader of the LIFE RCN, which is focused on the formation of early cells and multicellularity, focusing in particular on Earth, but using principles, properties that could be extrapolated to other systems. There's another one that is focused principally on biosignatures, in particular with an angle towards Mars. The Nexus program is focused on exoplanets, which is something very close to what we do. These are planets that are far outside our solar system around distant stars. And I'll talk a little bit more about that because that's what really dazzles me. It's likely that every star in the universe has planets around it. I'll talk about the numbers. It boggles the mind. Ocean Worlds is focused on things like Enceladus and Europa and the other liquid water-bearing bodies, particularly in the outer solar system. And this one that I'm involved with, which is called Prebiotic Chemistry in Early Earth Environments, which bridges the work that's been going on for decades, many, many decades, to try and understand how life began on Earth with an increasingly sophisticated understanding of what early Earth was like. And so if you think reaction X, Y, and Z, in the absence of life, may have led to the small molecules and precursor compounds that ultimately became something like RNA, then you need to know what the world was like at that time. And so it's been really exciting for me, and it's, it began when I was a PhD student. I studied the Black Sea, which is a special body of water on Earth. It's almost completely devoid of oxygen, so we think of the ocean mostly having oxygen, and lots of things are living in the presence of that oxygen. The Black Sea, because it's isolated, and it has a variety of things that have come together to make it so that just the surface 100 meters or so has oxygen, and the remaining 2,000 meters of water depth are free of oxygen and rich in hydrogen sulfide, that stinky gas that smells like rotten eggs. So it's a special kind of place, and it's in particular special because it's probably what the ocean was like over most of Earth history. The world we have today that is bathed in oxygen with 20% in the atmosphere and almost all of the ocean being fully ventilated and oxygenated, that was not the case for most of our history. And so that oxygenation may not have happened until about the last 10% of our history. So we have to study places that we have today. There aren't very many of them. We study them in detail to develop techniques that allow us to understand the ancient ocean and allow us to understand how life evolved in those systems and affected the atmosphere, in particular the alternative Earths that Frank was talking about, are these different conditions within the solid Earth and the liquid Earth, the exterior of Earth, but ultimately they manifest, are expressed through time in evolution of the atmosphere. And within that atmosphere are the greenhouse gases through time that kept our Earth warm, and we'll talk a little bit more about that, but also compounds like methane and oxygen that may have a direct relationship to life that was present at those times. And so the Earth has been many remarkable worlds, many alternative Earths spanning the 4.54 billion years of our history. And among the most remarkable things in science, I think, is that we developed the presence of liquid water on our planet about 4.3 billion years ago. We had oceans in our earliest history, which is really beyond belief when you imagine that the sun was only about 70% as bright as it is today. And so we can leverage that understanding of the sustained habitability. It is about tracking, understanding liquid water and what supports that and allows for the development of life and ultimately changes in the atmosphere that allow us to think about how we can look at exoplanets. And so it allows us, as it says here, to think beyond the solar system and these extrasolar exoplanets in particular. And so, again, are we alone and how did it start? So the question of how it all began is something that's been with us, I think, as long as we have any kind of recorded history. And so I sat down, as you all would do, and I started searching different cultures and looking at their genesis stories, their origin stories. And there are as many different stories as Wikipedia pages you open. And they all have some kind of universals running through them. They all invoke some kind of supernatural, for lack of a better term, way of originating life. In other words, faith-based in essence, that are not really testable. And we have Genesis within the Christian community, and the idea that it was created, that there was intelligent design and how life began and evolved. And there are subsets of that independently, because these cultures weren't interacting, that track a lot of the same kinds of ideas. And so that's one idea, and that certainly is something that would be pervasive even today within the community mindset. And I've been talking to many folks here during this visit about the struggle still to convince the general public in particular that evolution is a real thing and that the evidence for it is profound, and that it carries with it tremendous implications, not only for Earth, but how we think about life elsewhere. Because we're not only looking for life, but we have to imagine how life on Mars could have begun, and how it could have begun on an Enceladus or Europa or on an exoplanet. And so I had a really turning point in my experience. As a freshman, as a geological engineering student, there were not many classes that weren't math, chemistry, and physics and engineering. But I took one that was, Frank will know the book by a man named Jay Bernowski, The Ascent of Man, and there was a chapter on that, on the famous Miller-Urey experiment. And I didn't know anything about that when I was an 18-year-old. And so the Miller-Urey experiment was, Harold Urey was an extraordinary man, and he got a Nobel Prize for something other than this. What's that? He taught chemistry here? Oh, wow, there you go. Well, you should have that on the sign. Yeah, well, he was something else. In San Diego, he ended up at UCSD, and so my colleagues there will take me into the Urey room where you can actually see his Nobel Prize and a bunch of, and his old mass spectrometer is there. So he had a remarkable impact on people, and many of the famous post-war geochemists passed through the University of Chicago and were trained by Urey and Urey's people. And so Urey did some really pioneering work with isotopes, and that was enough for a Nobel Prize. But he had Stanley Miller working with him at the same time, and they probably sat over a coffee and said, let's try to imagine that warm little pond, that sort of early Earth environment as Darwin might have envisioned, or we can envision based on what we know when we're doing this experiment many decades ago. And they imagined a very reducing world, in other words, not oxygen-rich. Oxygen didn't come until much later. But in this little jar, they threw methane and ammonia and carbon dioxide, some hydrogen, and they sparked it to simulate the energy coming from lightning. And they created a vast array of organic compounds. People are still actually going through some of the laboratory apparatus of these experiments and finding more and more different compounds. So a broad suite of amino acids, things that are building proteins, things that we know are important. And we'll talk a little bit about this, but in fact, the experiment was flawed in some fundamental ways in that they didn't quite have the atmosphere right, or maybe it wasn't like that all the time. But it was an epiphanal moment for me, because here I am, 18 years old. I was raised as a Catholic, and I thought, okay, this opened a window of possibility to me. Maybe Miller and Urey weren't right, but now I started to understand the building blocks of life that are possible from creation in space and delivered by meteorites, or that can be produced on Earth through a wide range of processes. And I'll show you a couple figures for the complexity of these possibilities. We still don't know anything about how life formed, really. The Luca argument even would be debated, right? And so that's what makes it so exciting. If we knew everything and it was easy, you wouldn't want to do it, right? And so there are fundamental differences that range as wide as life began on vents deep in the ocean, high temperature vents like we have in ocean ridges, to those that argue for it forming on land surfaces that may or may not have been present with very strong deliveries from atmospheric chemistry. So what you have to imagine is you're fundamentally starting with an inorganic world that can generate organic compounds, whether they're delivered or formed on Earth itself, and how those come together, how those conspire to build increasingly complex molecules that might become a nucleic acid, might become a protein, might become whatever. And then once you have that, how you get to life to get to a metabolism, well, wow, right? So there's a lot left to do. But that changed my life, right? And I think that also what's happened in recent years is that as we've studied, my group and many others, these very old rocks, that we have at least solved Darwin's dilemma. So Darwin saw this great explosion of life about 540 million years ago. It's called the Cambrian explosion. And we saw many animals appear, a great diversity, some that are closely related to things that are still around, many that are extinct, like trilobites that you know, and other organisms. But the point was that Darwin could look at these animals within the rock record. He and others back in the 1800s were going through and looking at rocks stacked up and realizing that there's a progression of appearance and disappearance. In fact, the geologic timescale was devised originally not by dating rocks, that didn't happen until much later, but it was simply by looking at the presence and disappearance of fossils and correlating those over broad regions and realizing that this rock with this fossil suite is the same age as this rock far away with the same fossil suite. And so the geologic timescale that you've all heard of one way or another was really done by looking at this progression of life through Earth history, in particular over the last about 540 million years. And so a rich record of life, in fact, on Earth that goes back to, as Frank alluded to, maybe 4.1 billion years ago, convincingly 3.7 to 3.5 billion years ago. Luca, that's not a physical bit of evidence. It comes from genomic work, and that's really striking, and that goes back maybe to 4.2 billion years ago. So the Darwin dilemma is solved because Darwin couldn't imagine how there could be this explosion of life out of nothing. And now we know that there was much more than nothing, billions of years of life progressing from simple prokaryotic organisms to the earliest eukaryotic organisms, to multicellularity, to animals, and then ultimately the progression of animals that we have over the last hundreds of millions of years. And so What he didn't really know very much about was about the earliest environments. And so we still know very little about the origins, but we know a lot more about what the early Earth was like at that time and what was possible. We can put some constraints on how life may have begun simply based on observations of what the world was like. And so the clock in many regards begins at about 4.5 billion years ago. Within the first 100 million years of Earth history, we talk about big swaths of time like they're nothing. We're dealing with 4.54 billion years ago, and with the first few tens of millions of years, there was an impact by a Mars-sized object that spalled off material that became our moon. And so this impact was large enough that the Earth's surface was covered by magma oceans, and it would have been really inhospitable. So any life that may have begun before that, or any presence of liquid water, which was unlikely, that record would be lost, and you would basically start the clock again at this point. And so this is sort of the t = 0 as we think about moving forward. And so that time period associated with the moon-forming impact and that followed for the hundreds of millions of years following that, for most of the history of geologic science was thought to have been really a hellish place. In fact, it's called the Hadean after Hades, who was the Greek god of the dead and the king of the underworld. And so it's literally called that because we imagine persistence for long periods of time of not oceans of water, but oceans of molten rock, magma oceans. And so the moon was closer than it is now, and it was quite an extraordinary place. But what science has shown so remarkably in recent years is that it may have begun like that, especially it was like that associated with the moon-forming impact, but it became much more like today very quickly, within the first really literally tens of millions of years, 100 million years. And so I'll talk a little bit about that, including the idea that we had oceans very early on. And so when I first started doing all of this, one of the great challenges to understanding the beginnings of life is where the water was that these reactions were occurring in. Again, liquid water is the centerpiece of understanding sustaining life, but also the generation of life. And so there were remarkable discoveries that were about 20 years ago, and it's like, you know, there are these milestones in the history of life, in the history of the sciences that really changed the game. And so drilling these little sand grains that were found in rocks in northwestern Australia, using really sophisticated techniques, they've been able to analyze isotopes within these little sand grains of the mineral zircon and actually have argued for liquid water convincingly. There's not really much of a debate about this anymore, going back maybe 4.3, maybe even 4.4 billion years ago. So really soon after the moon-forming impact, we already had an Earth that was developing an atmosphere from degassing of the Earth's interior, that we may have had temperatures at the surface that were not so different than the temperatures that we have today, and that liquid water was probably persistent and probably pervasive. We had something like oceans, many people would argue. So that really gave you a world where you could do a lot in the most fundamental way with thinking about how life may have begun. Now, it's really hard to understand in the same way that it's hard to understand how Mars had liquid water early in its history, because the sun, as it was for Mars, going back to the beginning of Mars and Earth are the same age, the sun was only about 70% as bright as it is today. We live around a G-type star, and by looking at stars that are out there now, we have a really strong sense of stellar evolution. And so our star, our sun, is getting brighter and brighter and brighter, and here we are in that 4.54 billion years of evolution. It will get bigger and bigger and bigger, and it will go away, but tell your kids not to panic. That's a long time from now. But it continues to get brighter, and that has to factor into climate models that are spanning tens of millions and hundreds of millions of years, because the energy that we're receiving from the sun has fundamentally changed over these very long time scales. So the only way that you can really explain having liquid water on such an early Earth is by having an atmosphere that was loaded with greenhouse gases, CO2 and methane in particular. So today, we hear almost every day about the concerns that we have with the human-induced increases of carbon dioxide in the atmosphere, and we should be very, very, very concerned about that. We're about 100 ppm increase since the onset of the Industrial Revolution. Staggering. There's no geologic natural process that can yield that kind of increase over such a short period of time. So it's just clearly related to burning fossil fuels, and that started, and we have measures of that from instruments on land, but also using ice cores and looking at the inclusions going back millions of years. We can see what it was like, and then we can see that increase. So CO2 increase is a dramatic problem now, but thank goodness there was a lot of it around early on, and potentially methane, to keep the Earth warm enough to have those oceans that could support life in its early evolution. This is far too much to go into, but what I want to tell you is that the idea of having early methane, which also helped Miller and Urey, because they threw that in their little jar, that was the reduced carbon compound that was central in their understanding of generating organic materials like amino acids. It probably wasn't very abundant in that early atmosphere. And the main reason for that is now we know from really sophisticated and elegant geochemistry using isotopes, tungsten and hafnium. It's not really that important to go into the details. But what these systems tell us is that our core formed, like a lot of the other things that I've been talking about, our interior formed, iron moved through gravity from the outer portions of the Earth to the center of the Earth within the first tens of millions of years. So that did a couple of things. It created that iron-rich interior that ultimately became the dynamo that generates our magnetic field. How happy we are to have that, because that protects our atmosphere from solar winds and the erosion. We would lose our atmosphere otherwise. So that was put into motion very early on. But what also happened is that you're moving this metallic iron, and it leaves the outer portions of the Earth what we say is too oxidized. It was no longer a system that was readily able to produce things like abundant hydrogen and methane. Sure, they were produced, but not at the levels that would have sustained a methane-rich atmosphere. That changed a bit with studies that have been coming out in recent years. This is like ripped from the headline stuff. You're getting the latest and greatest. There is now an idea that large impacts, and they were large and frequent early in our history. Not as large as the moon-size impact, moon-forming impact, happily, but not far behind. And if you look at the estimates based on solar system models and looking at the lunar crater history, so Earth has recycled its surface all the time through plate tectonics, but the moon hasn't. And so when you look up there, you see all those craters, and they date back billions of years. We don't have surfaces like that on the Earth anymore. So what hit the moon when there was an abundant period of impacts, we can infer for the Earth as well, because we occupy essentially the same place within the solar system. And so we have really good sense of early impacts, frequencies, and magnitudes. And so it's possible that there were these iron-rich impactors that were bringing the material like we have in the core, and through that delivery, bringing it to the surface of the Earth, and through a series of reactions, generating hydrogen and then ultimately methane. We may have had pulses of a Miller-Urey type environment where methane was high. Maybe it was long enough to stimulate some of those prebiotic reactions that were generating building blocks. Also helped with the nitrogen cycling that you need in ways that I'll talk about in just a second. So this is like, it's like a tennis match. You think, no, it's too oxidizing. Well, maybe not. How often? And that's the way science works, right? It's this ever ongoing kind of iterative process towards some kind of well-accepted reality. And so the takeover, as it says here, the takeover of methane by biological production. So a lot of the methane on Earth, not all of it, but a lot of the methane on and near the Earth's surface today is produced by microbes, archaea in particular, and that didn't start until about 3.5 billion years ago. So early methane was through these non-biological processes. Again, it's a really important greenhouse gas, as methane, but also the CO2 that forms from methane. It's important today. We're producing large amounts of methane through rice paddies, livestock. As we heat permafrost, we're accelerating the release of methane. And so it factors a lot into climate change models. And it was really important early in Earth history. So what we're doing as we think about, as I've alluded to already, what we're thinking about is prebiotic synthesis of materials, right? Simple molecules, perhaps, and how we can bring these together into polymers that are longer chain molecules, and that ultimately, through a variety of different possible scenarios, generate things like nucleic acids. And we'll talk about this idea of an RNA world in a second. And eventually, once we get to LUCA, something that is life, something that fits the NASA definition of life, it was perhaps able to participate in Darwinian-type evolution, that needed energy, was able to reproduce, all those standard things that were life may have begun as early as 4.2 billion years ago, or maybe even earlier than that. And from that springs this incredibly complex tree of life that people are still sorting out, people here and at many places throughout the world. So the simple to the complex. And I had, again, we're lucky in our lives, the things, even at the time you don't realize what you're experiencing. I was at Yale, as Frank mentioned, as a graduate student, and I was taking the elevator up what used to be called Klein Biology Tower. I think it's now called Klein Science Tower. And so I'm riding up this elevator, and my advisor, Bob Berner, who was really respected in biogeochemical cycles, and he was really an extraordinary guy. And this guy got onto the elevator, and Berner said to him, "Well, congratulations, Sid." And we got up to the lunch place, and we got off, Berner and I, and I said, what was that about? And, well, it was this guy. It was Sid Altman. He had just won his Nobel Prize. And it was like, I think about that moment. I can still remember being on that elevator. I must have known that it was a bigger deal than I realized. So Sid was really, so he won his Nobel Prize in 1989. He was from Canada, but spent a lot of his time at Yale. And it was for the discovery of catalytic properties of RNA. So there are probably biologists in the room that know more about this than I do, but the RNA world is a really popular, not universally accepted, but very popular and widely explored view for how life began. And the basic idea is it's a gene-first model. Because we have this chicken or egg conundrum, as it's talking about, as you think about building these initial, more complex molecules that become the foundation of life, like RNA and DNA, we have proteins that require DNA to store the information for the construction of the protein, but DNA requires protein to do biogeochemical work. So you need something that's doing work, producing energy, but at the same time, to produce those things that are doing that, you need things like DNA and RNA that are storing information. So which came first, right? How do you have the catalysis that's supporting the DNA activity, or do you have the DNA that's there to build the proteins that are accomplishing that? And so what Sid recognized, I think brilliantly, was that RNA could do both, right? That it was really this extraordinary thing. And so that RNA could function in essence like a protein, catalyzing reactions and building materials, but at the same time, RNA could transfer information. So early forms of life may have relied solely on RNA to store genetic information and to catalyze critical chemical reactions. I don't think Sid had any idea that he was spawning the RNA world for the beginnings of life, but it was quickly adopted in that way, and RNA is a remarkable material. And so this is what some of the modern models look like, and I'm showing this purposely because it's so complicated. I want you to imagine this day, 4.3 billion years ago, where you had an impact that was generating those reducing conditions because the core had formed already, and that impact was generating things like nitrogen compounds that could ultimately, like nitriles, hydrogen cyanide, that could ultimately become the nucleobases as you're starting to build towards nucleosides and nucleotides and nucleic acids, land surfaces that could allow for polymerization reactions, so many different things happening in this very complex world. And so the reactions are really quite remarkable. So you have these nitrogen-bearing base pairs, these nucleobases, and so these are combining with sugars, ribose or deoxyribose, and they're creating the nucleosides that then go through an addition of phosphorus to going from a nucleoside to a nucleotide. Now, what you have to look at in all of this is like this process right here has been one of the great vexing issues in understanding how life has evolved. The addition of phosphorus to go from a nucleotide to a nucleoside to a nucleotide, and then how these can ultimately, in complex ways, be, through purely abiotic processes, lead to something like RNA. And so the phosphorus addition, what the atmosphere was like, they're all sort of nested within this very complex day in the life, early generation of life on the earliest Earth billions of years ago. So I've been trying to think in a most fundamental way as I think about the RNA world, but other worlds as well, like what was going on those days 4.3 billion years ago? What was the Earth like? And so many of the reactions and models for the beginning of life, including the RNA world, involve the idea of having exposed land surfaces. And so what happens when you take compounds that are existing on a land surface, or in a pond on a land surface, the idea of letting them wet, perhaps during a seasonal wet time, and then dry and wet and dry, or a tide, the water comes in, the water goes out. What experiments show very convincingly is that as you go through these cycles of wet and dry, whether tidals or seasons or in a hot spring, that you can take relatively simple molecules and generate more complex biopolymers. So you can start to go from the simple to the complex simply by wetting and drying. And the results to simulate this in the lab are really quite remarkable. But the problem is that if most people are right that work in the geologic community, there were no land surfaces to do this. There weren't places for the hot springs to sit in a pond, the warm little ponds. There weren't areas for tides to wash up onto a land surface and then back into the ocean. And so when colleagues first started telling me about this and I was learning more and more about these different scenarios, I would simply say, look, here's a very complex figure, and each of these curves represent work by a different person. But what they're almost universally telling us is that the production of continents, land surfaces, and the emergence of land above the oceans went on for a very, very long time, for hundreds of millions and maybe even billions of years. So it is actually really difficult to imagine a world anything like today in terms of land surfaces sitting above the ocean that could participate, drive these wet-dry condensation reactions. So people are responding, right? And one idea is that these impacts that are doing a number of other things could have created giant craters with rims or central highlands that could have been emergent above the ocean. Or another popular idea is that you had hot material coming from deep within the Earth, much like we have today to generate the Hawaiian island chain. So these mantle plumes, as they're called, that may have come through much of the Earth and pierced the surface and generated what are called hotspot volcanoes, like the Hawaiian Islands. So we still had the way of generating, at least in a quasi-long-term way, not only masses of potential land, but land that could emerge, as this image shows, above sea level. But that's how you have to do it, right? If you're proposing a chemical sequence, a reaction network that requires wet-dry cycles, then you have to tell me as a geologist how you can do that when you're 4.3 billion years ago, and by most models for the tectonic evolution of Earth, we didn't have land. That's just one example, and I'll give you a couple of others. This is what that impact history might have been like. So this is spanning a period from 3.5 to 4.5. It's again based on observations of the moon, but it's also based on our understanding of what was floating around in the protoplanetary disk, and ultimately as planets were starting to form, there was a lot of residual material flying around and hitting Earth and hitting other planets. So I have been this big proponent of what I call the impact of impacts. And so this is just a very quick list of, some of you will know that the dinosaurs, which became extinct about 65 million years ago, that extinction is largely attributed to an impact off the Yucatan Peninsula, the Chicxulub crater, right? That's been explored. It's well known to be a potential killing mechanism for the dinosaurs. So we tend to think as geologists as impacts are driving bad things, extinction in particular. But early in our history, there were a lot of beneficial things that may have occurred, particularly for the production of life, delivery of organic compounds, a crater topography for wet-dry cycles, greenhouse warming by generating that methane-rich environment, hydrothermal activity, hot fluids that are running through the rocks because of this large energy impact, delivery of reactive phosphorus. Remember, I said it's so hard to understand that process called phosphorylation, where you go from the nucleobase that's combined with the sugar and add a phosphorus onto that and go from a nucleoside to a nucleotide. And so there are reactive compounds that come from meteorites that are much more reactive with organics than the common form of phosphorus in the ocean, which is phosphate. So it's called the phosphorus problem, because the phosphorus that we know of in the ocean is nowhere near the concentrations required to drive that reaction in the absence of life. And so when people do it in the lab, they do it with concentrations of Earth-like phosphorus that are orders of magnitude higher than in the ocean, many orders of magnitude. And they say, well, that's what you have to do. And I say, but that's a problem, right? And so people are turning towards other alternative phosphorus pathways, delivery of bioessential trace metals that are important, for example, in many enzymatic reactions. And so By roughly 3.5 billion years ago, even though life may have originated much earlier, biology really began to flex its muscles. It was producing methane, so all the phylogenomic data support the idea of methanogenesis initiating around 3.5 billion years ago. So we had changing environments, we had biomass, organic material produced through these biological reactions, mostly through microbes. We had microbial innovations and proliferations. And we had biological controls on the cycling of methane, nitrogen, sulfur, iron, trace metals, and eventually the production of oxygen for the first time at about 3 billion years ago by life, by photosynthesis. So again, these are big numbers, right? That's 3 billion years ago, but a billion and a half years had already passed before we got to the point where cyanobacteria were producing oxygen. So that's why I say the ocean for most of its history was devoid of oxygen, and the atmosphere was devoid of oxygen for about half of Earth history. And so the early atmosphere, as life was beginning to really kick in, especially these microbes, archaea, that are producing methane, there are many people that think the Earth, rather than being the pale blue dot that Carl Sagan famously referred to, that it was the pale orange dot. And that the oceans may have been green because the iron was mostly reduced rather than the iron that we have today that's mostly insoluble in the presence of oxygen and not very rich in water. When there's no oxygen, you can have plenty of iron around and it can be green. So we may have had a world, if you took your time machine back, we may have had a world where you would have stepped out of the time machine to green oceans and orange skies. This is not unlike what we have around Titan today, right? Organic hazes that form from things like methane and other organic compounds. Titan, which is a moon around Saturn, has lakes of liquid methane. Right? It's really quite extraordinary, and other organic compounds. And we sent a mission there, or will send a mission there soon, the Dragonfly mission. So I published a paper along with colleagues this past year where we sort of looked at the coevolution of environments and imagined what life was doing along the way. And so this is my famous, infamous oxygen curve in its latest manifestation. And so here we are at about 2.5 billion years ago, and only then did oxygen start to experiment with injection into the atmosphere and at least being around transiently. It was first produced by biology, if we're right, about 3 billion years ago. But as quickly as it was produced, it was consumed by reactions with rocks on the surface and gases in the ocean and gases in the atmosphere. So there was a buffering, we say. It took hundreds of millions of years from the initial production to get to the point where that balance was tipped towards accumulation of oxygen in the atmosphere. And so that's something that's actually called the Great Oxidation Event. So if somebody says, what about oxygen on Earth? Say, well, at about 2.3, 2.4 billion years ago, we initiated this fundamental, maybe the single biggest, anyway, biogeochemical transition in Earth history from a world without oxygen to a world with oxygen. So think of all the life on Earth today that requires oxygen, aerobic metabolisms, the high energy that comes from a microbe that has accessibility to availability of oxygen. That didn't exist. It was an early world that was devoid of oxygen, and then things really changed. We still have many portions on Earth within sediments in places like the Black Sea that don't have oxygen. So we have a coexistence on the planet today of oxygen-requiring organisms and organisms for which oxygen is toxic. So the niche space expanded and the diversity of life on Earth changed fundamentally. And so we are been looking as a group at these different pathways. Here's the cycling of nitrogen going from N2. That's converted to what's called fixed nitrogen that can be used by a number of organisms. And as oxygen became more abundant, and that reduced nitrogen could be oxidized and returned. So it's cycling constantly, but what you'll get from these colors, just the one critical thing is that this represents time. This was the earliest time, later, and that's much later. So initially, the nitrogen cycle was partial. It was doing some things and not others, and it may have affected the total pressure in the atmosphere. So our atmosphere is so intimately linked to life and to the processes within the oceans. We had oceans, and now we increasingly had life within those oceans, and it may have looked something like this. This area that's brown is portions of the ocean through time, from 3.5 billion years ago to today, that were dominated by a lack of oxygen and a presence of iron, dissolved iron that was really abundant. And it's only this blue stuff that's where the oxygen was. There were little bits of oxygen, maybe early in our history, transient, not long-lived, and then the surface ocean persistently oxygenated, and it was actually relatively recent in our history, maybe 400 million years ago, that the full ocean oxygenated other than places like the Black Sea. So what you're getting from that is that the Earth has changed a lot. And life has been driving those changes and responding to those changes. And through all of that, the atmosphere has been changing. And the atmosphere is containing for the first time, starting at 2.3 billion years ago, oxygen, which is a quintessential biosignature. You look at that oxygen, you know it's from photosynthesis. Methane, starting at 3.5 billion years ago, is accumulating in copious amounts within the atmosphere derived from microbial activity. So again, think about these exoplanets. We're never going to go to them, and I'll talk more about them to end the talk. We're never going to go to them. They're light years away. And so as we explore and spend vast amounts of money trying to ask that fundamental question, are we alone, it's going to be through the characterization of atmospheres. And Earth is helping us understand how atmospheres can evolve and how atmospheres can reflect the processes of life that are occurring within the environments beneath. So our alternative Earths are many different slices of Earth history that give us evolving atmospheres that contain, in varying ways, signatures of the life in the waters beneath. And so it's a cause and effect relationship. Environmental change drives biotic change and vice versa. And there are profound, profound things that have changed through Earth history. So if we went in our time machine 1 billion years ago, if we went 700 million years ago, you would see the Earth covered mostly with ice. Other times you would see mostly water and no land. You wouldn't recognize it. And so as we think about optimizing the utility of ancient Earth to fulfill NASA's mission, it's building together, as Frank alluded to as well, this catalog of different planets that ours has been to increase our toolbox, our search engine, as we think about possibilities elsewhere. And that elsewhere that really drives, and I'll end with this, that really drives a lot of what I care about, is extending it to exoplanets. Now, these are extrasolar planets. They're planets around stars outside our solar system. And this is just a famous artist version of what these things might look like. We have, every time I give a talk, whether it's just a couple of weeks between talks, I have to update this slide because the discovery rate is so fast. We have what's called the Transcending Exoplanet Survey satellite that's out there now looking for these planets. And so just within a month period, it went from almost 5,800 now to over 5,800. And they're detected in a variety of ways, and I'll show you a very simple cartoon of that. And so, again, as we think about exoplanets, the biosignatures, if found, are almost certainly going to be atmospheric expressions of microbial metabolisms in the water beneath that atmosphere. So when I say to groups, will you be excited when I tell you 10 years from now, if we're lucky enough, that we have found methane around an exoplanet 3 light years away that within 99% certainty derives from the activity of archaea microbes? Will you be excited? Or does it have to be a green person knocking on the door saying, let me in? And to a person, they're excited about the microbiology just as much because it means no longer in the world are we the N1 planet. And then that opens up in a remarkable range of possibilities. So this is the thing that maybe will blow you away the most. There are 10 to the 25 planets within the universe. So that's 25 zeros, right? And so that number doesn't mean anything, but I tried to put it into perspective. 10 to the 25 thimbles of water would be required, thimbles worth of water would be required to fill the Pacific Ocean. So that's a lot of planets, right? And you can say with that many planets, then surely there must be life elsewhere. And I can't challenge you on that. It may be that Earth is a very, very special place, and we're very lucky to have it, and we should be damn more careful about how we treat it. But it begs all sorts of possibilities and questions. And there are a lot of planets. Our focus will be on planets that are within our own galaxy and close, right? It's really, we can see other galaxies, but we can't really see planets within them. So the focus is on our nearest neighbors within the galaxy, and they're still light years away. And so there is this idea of the habitable zone. That's what we really care about. We have gas giants in our outer solar system. We have the rocky planets. Venus is almost exactly the size of Earth. It's a rocky planet. If you were looking at it from light years away, you'd say, that looks like a good place to look for life, until you looked at its atmosphere and realized that it's on the inner part of the habitable zone. It lost whatever water it had. It has temperatures of between 400 and 500 degrees C, and it has 100 times the pressure that our atmosphere has, from mostly CO2, but also sulfuric acid. It's not a very nice place to live. And so we can use our own comparative planetology of Venus versus Earth versus Mars. They probably all around 3.5 billion years ago, by many arguments, had liquid water and could have generate and sustain life. Mars and Venus went awry for very different reasons, and Earth sustains, right? And that's a remarkable thing that we keep this water around for so long. And so the habitable zone is defined by the range of, the distance, it's a zone from a given star in which the planet has the right kind of combination of distance and brightness of the star to sustain liquid water. So it's the right, and so it was very commonly referred to as the Goldilocks zone. If you're too close, it's too hot. If you're too far, it's too cold. Whatever water is frozen or it's lost because it's super hot. So it's just right. And that, again, is based on how bright the star is, how far the planet is from the star, but there's another critical component in that, as it was originally defined and it's still used, is the composition of the atmosphere. Because I've already told you that Earth's history of sustained liquid water is very closely tied to what's in our atmosphere: methane, carbon dioxide. And so the definition of the habitable zone, as widely used, includes inferences, assumptions really, about the amount of carbon dioxide as you go across the habitable zone. And so we can identify these planets simply by their transits across the star that they're orbiting. So this is actually time-lapse of Venus transit in front of our own sun. So that's Venus. And you say, well, that's a really small planet relative to the star, but the instruments, mostly telescopes that are in space, things like James Webb and others, the instruments are sophisticated enough that dimming of the starlight coming to us is enough from the planet eclipsing across the star that we can identify the planet. So most of the planets are identified by what's called transit. There are other techniques. One is called radial velocity, so the star and the planet interact gravitationally. So there's a time where the star is nominally moving towards us versus away, and so you get a Doppler shift. You get a red-blue Doppler shift, and it gives us mass. And this gives us the size. If you have size and mass, you can suddenly make an inference about the density. This is light years away, right? We can't even see this planet. But through this indirect evidence, we can make inferences about what kind of planet it was, how big it was, where it is within its habitable zone. And we can start to say that might be a target where we want to go and see if there's liquid water, and then start to try and target it for atmospheric characterization. So this is the famous TRAPPIST system, which is a 7-planet system. And so this is full brightness from the star, and you see these periodic, literally periodic dips in that as the different planets among the 7 are passing in front of the star. So we get a sense for how quickly it goes around, how many there are. It's a very complex kind of gravitational dynamic system to imagine how these things, all as close as they are to one another, stay in stability and orbit the TRAPPIST star as they are. But there's a lot of focus on that. But in addition to getting the idea that there is a planet or multiple planets, when it's transiting across, remarkably, there's some amount of light that passes through the atmosphere around that planet. And when light interacts with gases in an atmosphere, there are absorptions that are of the light at specific wavelengths that are associated with whatever gas is there. So let me say that again. When an exoplanet passes in front of its host star, from our point of view, a small fraction of stellar light passes through the exoplanet atmosphere. That's what we're seeing, this blue thing, where molecules absorb light at some wavelength that relates specifically to what gas is present. So we're literally looking at spectra with sophisticated instruments where we can see dips that correspond to CO2, to methane, to whatever gas is present there. And that's how we're going to, if we will, find atmospheric biosignatures. And so there are many different kinds of biosignatures that people focus on. There is a great concern about the false positive. These are features that we might attribute to life that are not associated with life. Methane that's produced through a planetary process rather than biological process. Oxygen that's produced from the photochemical breakdown of CO2 as one possibility. And so we're first trying to find these gases, and we will with increasing precision and frequency. But then that just starts the grand challenge of trying to figure out whether that O2, that methane, that ozone, O3, whether those specific gases are likely, possibly, or must be related to life. And so Earth has taught us some interesting lessons that are partly scary. Oxygen began being produced by biology about 3 billion years ago. And initially, as I said, the anoxic ocean persisted, well, actually for very long periods of time, and the atmosphere had low amounts of oxygen, was anoxic, and so the oxygen was originally confined to the surface portions of the ocean. And so you would not have seen that by a telescope. It's not in the atmosphere. You wouldn't have seen the spectral signal of oxygen because it simply wasn't there. Yet the ocean had surface oxygen. It was supporting aerobic metabolisms. It was changing life fundamentally, but we wouldn't have seen it. So that's a false negative. It means we're basically missing the life that's there. And we worry about that, and people used not to talk about that very much. And it's reasonable to imagine that the biological production through photosynthesis of O2 may have predated its detection, were you to be looking at Earth those billions of years ago, by almost 2 billion years. Right? So we may have had development of all of this life and evolutionary innovation for 2 billion years before the oxygen gave up its secret and started to be present at detectable levels within the atmosphere. So what that means is that we have to think about more and more clever combinations of gases and other gases to look at. And there are hundreds, if not thousands, of scientists around the world that are focused fundamentally on developing a variety of biosignature scenarios. For example, we wrote a paper not very long ago where we looked at the seasonality of oxygen and CO2. The curve is increasing dramatically from the burning of fossil fuels, but superimposed on that are these subtle seasonal variations that relate to hot, cold seasons in the northern hemisphere and plants on land. When it's warm, plants produce a lot of oxygen through photosynthesis and are consuming CO2. When it's cold, they do less, the leaves fall off, the leaves are degraded, and so they release CO2 and consume oxygen. So they're antithetically varying across a year. And so it's possible to imagine a low enough baseline level of CO2 where you could see that seasonality. Now, these are thought experiments, but they're things that could be detected, especially as you envision what telescopes and combinations of telescopes will look like 10 years or 100 years or even 1,000 years from now. And so it's, I was saying earlier, I would sit down with my sons and say, if you were looking at our atmosphere today, what would you be able to tell about life on our planet? You would see the chlorofluorocarbons, so you would see that as a technosignature because we were putting those in cans for a long time. That signal is going to go away in about 40 years. We're fixing the ozone. There was the Montreal Protocol signed, and we don't do that anymore. It's a great example of what 198 nations can do when they actually are unified in their desire to fix things. If only we could do that with carbon dioxide. So that's a great technosignature. It's in a more advanced quote-unquote civilization that's releasing these compounds. The seasonality, there are nitrogen compounds. There's a wide range of, and so it's no shortage of creative frontier to explore these possibilities that could be detected and could be processed in a convincing way as being related to life. And so the traditional view of Earth is that we have methane early in its history, especially when produced by biology, those orange skies. That would have been a really great biosignature up until about 2.5 billion years ago. So if you were looking at Earth from a more advanced civilization, light years away, you might have said that methane is high, and it's hard to imagine that being produced by non-biological processes at those levels, especially when there's no oxygen, no ozone shielding. The methane breaks down through photochemical reactions. So this is what atmospheric modelers do. They say, how much methane fluxing into the atmosphere do you need to sustain a detectable level, and does life have to be required to do that? O2 is a wonderful biosignature on Earth, particularly our relationship to a G-type star rather than being around an M star where you can get a lot of photochemical production of O2. So we have O2 now, and we have methane back in early Earth history. It was long thought that there was a middle chapter of Earth history where we would have seen both. And that is like a gold standard for biosignatures because methane and O2 are not happy together, right? The methane breaks down, it oxidizes. And so to be able to have them in detectable coexistence almost certainly relates to the biological fluxes that supported that. But what our work says, and I haven't gone into this, but we have a series of papers that argue that methane was pretty low during this time period, and certainly oxygen was. So we may not have had either of those gases separately or the combination of them. So this was a great false negative. This is the time period in which eukaryotic life first developed, multicellularity developed, and it ended with, right here, with the development of the first animals. So there was so much biology going on, and we may not have had any biosignatures that would have tipped someone looking at us at that time that was happening. So as we think about all of this going forward, what my team is particularly interested in doing is finding life, But I think on the shorter term, what we're trying to do is inform telescope design. There is right now a massive effort within NASA to design what's called the Habitable World Observatory, which will be optimized for the characterization of atmospheres, and in particular wavelengths that speak to these various potential biosignature gases. So those wavelengths have to be chosen based on the gases that you think are most important. You can't measure all of them. So the telescopes just can't be designed that way. So is O2 ozone most important? Is methane most important? Is N2O most important? The red edge, as it's called, that's related to terrestrial vegetation. What portion of the visible spectrum do you have versus the infrared versus the ultraviolet? These are literally conversations that are happening right now. And people are arguing, saying, no ozone, no methane. And, in the end, there'll be an incredible vetting of that process, and the community will speak and say, this is probably the best thing to do on this multi-billion-dollar telescope that will hopefully be launched within the next 10 to 20 years. So it'll be like Webb, but times so much more because of the direct imaging capabilities. So this idea of being able to look at a planet directly, and the way that technology works is, one of the ideas is you launch in tandem with the telescope what's called a star shade. And so if we're outside on a sunny day and you heard an airplane and you looked up and the sun is just overwhelming you because so much of the energy is coming to you from the sun, what's the first thing you do? I'm looking here. You block it with your hand, right? And then you can see the plane, because most of that light is coming, not reflected off the plane, but from the sun itself. So what the star shade will do, potentially being thousands of kilometers away from the telescope itself, it will literally fly like a shade and block the planet so that we'll get a direct image, or block the star so that we'll get a direct image of the planet. So we'll get much better information about atmospheres. What I really get out of this most, and I think Frank would agree, is the extraordinary technology that's developed at places like JPL and Goddard. The engineering boggles the mind. Anybody who saw the sky crane lower Curiosity and Perseverance, you just can't believe it's real, but it is. And so these things, if you ask them, they will build them, and they almost certainly will work quite remarkably. The sample return is not for shortage of engineering ingenuity to do it. It's trying to do it within a time frame and a budget that will be acceptable by Congress, basically. So I think that's all I have, and I just want to end with these couple of things. Like I thought Tim was going to tell us that they found life on Enceladus. Yeah, no, I'm not, sorry. I'm not going to tell you that there is any evidence for life anywhere else in the solar system or universe right now. I can tell you that lots of really clever people are trying to figure out how to best do that. But along the journey, we do so much more than just, the prize is not defined necessarily by the discovery of life, but the things that we learn along the way. And so, the universe is complex, and it's not going to give up its secrets easily. And so Neil deGrasse Tyson said the universe has under no obligation to make sense to you, right? And so there are many things we don't know, and we should expect not to know them until we spend enough time to try and figure them out. The Richard Dawkins quote, "The universe does not owe us meaning," right? And so if you're looking for the great truths, it's great to look there, but I think the great truths lie in the journey rather than the destination. And so this is Tim's quote. "But the greatest joy comes from the looking. Even if the mysteries outlive your journey, and if we are really lucky, we stumble upon something unexpected and remarkable along the way that brings us one step closer to understanding who we are, our place in the universe, and whether there is a possibility of life." So I'll stop there. I think that's the last one. Thank you so much.
Any questions for Tim?
Let me ask you a question. How many of you think that will find signs of life within your lifetimes? And how many of you would be excited if it were just a metabolic byproduct of a microbial reaction? You would, right? You don't need a knock on the door of the spaceship, right? I just read this story recently, and it was so frightening, this world we live in. So there's this idea. There was a collection of sites on Earth. They're mostly archaeological sites, and they're under particular protection right now. Many of them are under threat from wars, to be honest, or sea level rise, or things that are human-related. But the moon was on that. And I thought, the moon? Well, because there are more and more missions planned to the moon. by countries other than the U.S. And there is a genuine risk that someday someone will go and collect the Apollo 11 flag and sell it on eBay. And so these are great historic sites. I'm not saying anyone's really going to do that, but you have to anticipate these things. And so it's, it's as other countries, ESA, the European Space Agency, ultimately it takes a village to do this stuff, right? And the more countries that are involved, the sample return mission with Mars, there's very strong buy-in from the European community because it's a lot of money and everyone stands to benefit. When those rovers launch, it's not just a rover that's supported by a PI and a team. Each instrument has its own team, in many cases very large teams, and they're monitoring the data that are coming in and integrating that with data sets that are coming from others. And there's remarkable opportunity for early career scientists, so much. It's amazing as I've watched my own students who want to get more involved in something, how easy it is to do that. Summer programs, internships at places like JPL, if it doesn't burn down, came close. And so if you have anything more than a casual interest in space, the NASA website resources are phenomenal, and the images are actually public domain, whereas our journalist friend, you can use those without permission. That's not very common, actually. So I'm a big fan of NASA. And I think that as things change, Frank and I hope dearly that NASA doesn't mess up what it does, not just for us. I was in China when the Curiosity rover was deployed. And I was sitting there and we were all literally crying watching this thing because it's think of the years of investment to get to that point. And then if it just we lost signal. And they felt the same pride. Not as Americans, but as people on a planet that are looking to explore. So, I think we're in a time of great exploration, and I think that the fundamental goals change in a way, prioritization of a moon versus Mars, but it's sort of it all kind of ends up in the same place in the end, right? And as I say often, it crosses the political aisle better than anything I know, right? Some of the strongest interest in Europa was coming from a highly conservative congressman from Texas. And others have their pet projects. And so it's one of the few things that we can these days agree on, that we care about who we are, where we came from, and how we can learn more and more and more and get a deeper sense of who we are through that process. So that's very heartening to me. It's not politicized in a lot of ways that other things are. So, any questions about, Enceladus, Europa? Do you have any of you space junkies enough to have a preference over which icy moon? I can tell you Enceladus. The plumes on Europa are not as well known. Enceladus in the southern hemisphere, those were enhanced images, but those are real images of plumes. Can you imagine? Cracks in the ice, this ocean coming through with hydrogen and organic compounds that are produced in the ocean beneath. An orbiter can fly through that or near that with spectral capabilities and actually tell us what's in that plume. Maybe finding, if we go through it with the right instruments, organic compounds that are not just potential building blocks of life, but are actual products, biomarkers, we call them, of life. That's all really entirely possible within the next couple of decades. There will be an Enceladus mission within the next 10 to 20 years. Watch for the Dragonfly mission in Titan. That's otherworldly stuff. Watch to see what happens with sample return. Watch as the community discusses when and if we'll go to Mars and plant a flag on Mars. Mixed feelings about that. It's great to have humans on Mars to try and do science, but there's always a risk of contaminating it. It's the planetary protection issue. And I think, and I've talked about people with this, and I'm asked about this all the time, I do not think that moving a substantial portion of our civilization to inhabiting Mars is a solution to what we've done on Earth. So I think to our Earth. So we need to be better shepherds of this very special planet that we have and view Mars as an intellectual curiosity and an idea of understanding how things can begin and change. But it's not going to be my next address, right? And I don't think it ever should be. But there are people who dream of that. But yeah, anyway. So, yeah.
I'll add something to Tim's quote. There was the Dawkins quote, and there's Neil deGrasse Tyson. What you're describing puts me in the mind of. Tim referred to the opportunities for young investigators to get involved in this, and so many young investigators who are on missions will be old women and men when the data start coming through from those missions. And that's the nature of the field. But the fact that people in this line of work are so excited about this, it kind of reminds me of cathedral building in the Middle Ages.
Think of Barcelona and Gaudi. It's been going on for 100 years.
Had, human projects, engineering marvels that required not a lifetime, but generations of human beings to achieve. I see it as completely analogous.
I do
to
too.
that.
The initiators will never see the final product. I may never see signs of life from an exoplanet, but I'd love to think, as I'm lying on my deathbed, that I contributed to a discovery that could happen. Frank's point is that some of these missions, they take 10 years to get to the planet, right? And so you see the big headlines, especially the outer solar system, all that exciting work that came from Pluto. It's too far to power those spacecraft with photons from the sun, so they have nuclear power generators, and so NASA's ramped up its investment in that by producing more plutonium. So the outer solar system planets are of great interest as well. Not that Pluto's a planet, but you know what I'm saying. It was. So it's like, you work for a decade to develop proposals that's strong enough to submit that might be chosen for a mission, right? And then it takes a decade to build that, and then it launches, and it takes a decade to get to where it's going. And then the data start coming back, and you might be gray and withered at that point, but you know that whatever people are seeing and discovering, you made happen. So it is a great place to be. It's really changed my life. I think Frank would agree. I stumbled into NASA, and the last 10-ish years have been quite extraordinary. Yeah.
I maybe should have thought about this before coming tonight. But kind of that line of the building blocks of life.
Yeah.
So what is life? And
Yeah.
Oh, sorry. What were the rest of NASA's?
What are the
ideas
criteria?
Of well, not the building blocks, but what makes something alive.
So Frank can chime in on this too, but there were entire workshops that still happen about what life is. And so there are fundamental things when I teach my class is that there's reproduction. So if you're generating something that you're causing life or calling life, that it has to reproduce and have some kind of persistence. It may go away eventually. It's participating in a metabolism, so it has an internal generation of power. And it also uses energy resources like the sun if you're participating in photosynthesis. It has to have building blocks. So carbon is used on Earth for good reasons. It has a particularly favorable bonding capability to build large, complex molecules. Silicon maybe, but carbon is better. So you need energy, you need building blocks, you need to be able to reproduce. And the NASA definition includes that whatever you're observing is participating in Darwinian evolution, that it's responding to environmental change and going through change in response to things. There is also this basic idea of basically the entropy of life, and Frank can speak to this, is that we're mostly reduced carbon in a world that's full of oxygen. Like, it takes a lot to be who we are. Cells have had to adapt in remarkable ways to deal with the oxygen that we also benefit from through respiration. There's a thought that very early in Earth history, there were geological processes that produced these superoxides that the earliest forms of life may have developed enzymatic capabilities of dealing with these, so that suddenly when there was oxygen through this biological production, they had inherited this capability that was purely a geologic happenstance before that. And so this idea of trying to live in a world that is not necessarily in thermodynamic equilibrium with who you are. So we maintain our body temperatures within a degree or so, right? It doesn't matter if it's cold outside or warm. We do that through our metabolisms. So that is a definition of life too, that we create our own environment that's sustainable, and it can adapt to external changes. And we have to feed it, we have to fuel it, but we can do that. And that's what the homeostasis, right? That's right. That's the homeostasis turn. And that's a remarkable thing, and that I think, in my mind, would be a fundamental to what life is. Yeah. So it's, but there might be other people that would disagree, and we're heading into Like, in the age of artificial intelligence, when does that start to become something that's like life? I don't know. You'd have to ask the Terminator. But yeah, I mean, it's a really brilliant question, right? And then I always get the question, and I'm sure Frank does, we're basing a lot of this on life as we know it. What about life as we don't know it? And that's hard, right? There are people who do that, whether it's silicon-based life forms or things that have fundamental different requirements for energy. I would say that at the end of the day, that almost everything that we talk about with life is basic physics and chemistry. It's not biology, it's physics and chemistry. And so those are going to be universals, right? You're going to have a way of producing energy. You're going to have a way of doing the things that we were talking about. And I think any life we form, maybe it's doing it in a slightly different way or a fundamentally different way, but those things are going to run through. And what we're so dependent on in looking at the history of our own planet are the remains of life, whether it's a metabolic gas in the atmosphere or a fossil or the earliest signs of life. It's such a remarkable thing. The earliest records of life in almost every metabolism that I showed you are isotopic. So I can give you a simple example of this. When carbon fixation occurs through a process like photosynthesis, the carbon that's produced is enriched in the light isotope. You know what isotopes are? They're atoms of the same element that differ in the number of neutrons. They have different masses. So when CO2 is processed through photosynthesis, the bond between carbon-12 and oxygen is easier to break than the bond between carbon-13 and oxygen. So the organic material is fundamentally enriched in that light isotope. So the earliest records of life, besides genomic arguments for Luca, the earliest evidence for life occurs in those little zircon grains, and it's not widely accepted, but it's graphite because it's been so altered through time that's enriched in carbon-12. So, you say, well, what do we know? It's not a microfossil, it's not a footprint, it's literally a light carbon enrichment in what's now graphite that may have very well related to a biological fixation process. Now, there are inorganic processes that can do the same thing. There's always that risk of the false positive. But you can look in context and start to address those things. The earliest evidence for sulfur cycling is isotopic. The earliest evidence for nitrogen fixation, denitrification, nitrification, it's all how these biological processes distinguish among different isotopes. And life has this wonderful consistency of favoring light isotopes of, again, a given element. One of the great challenges is that we don't have isotopes of phosphorus, so we're more constrained in how we can interpret that, but nitrogen is wonderful, sulfur is wonderful, oxygen is wonderful, hydrogen is wonderful. The hydrogen fractionations are huge because it's such a light element. So it's, whenever I teach and I talk to journalists, they're like, no, I don't want to hear about isotopes, but you have to. Because the evidence for life on Mars could very well be an organic molecule that's called a biomarker that's specifically attributable not just to organics, but to a life form. We have organic molecules today that we find in very old rocks that we can say are from cyanobacteria that produced oxygen, or archaea that produced methane. So if we're really lucky, we'll find one of those on Mars, but those records don't extend very far back in Earth because of the alteration of rocks. Mars actually hasn't had the same offenses of plate tectonics, so there is an argument that it may have better preservation of those things, ironically. We might learn more about earliest history of our near neighbor and our own planet by looking at Mars. But more likely, in my opinion, what we're going to see is a unique isotopic expression in methane or some carbon compound or sulfur isotope relationships that reflect a metabolism. It's all about these metabolisms and what they do to elements and how they give us diagnostic signatures or not of a biological role in their processing. And it's just the way it is. And I say that with exoplanets too. Wouldn't it be remarkable if we had a capability of getting isotopic measurements of the gases that we discover? And people say, oh, you're crazy, Tim. But it's actually possible. There are, within the spectrum, there are specific bands that can be tied to specific isotopes. And I've seen models for what these systems might look like, hundreds of years from now. It's like a sky, so it might be 1 million miles away out there. And it's good to get away from the planet, right, because we have a lot of background light. And so there are land-based, Earth-based telescopes that do a lot of this work too, but a lot of the best data are coming from things that are out there. And so I've seen these images of just giant arrays of telescopes, giant telescope mirrors that are out in space that are flying in coordination and collectively sending their signals back to a single collector. So imagine what you could do with an atmosphere and that kind of thing. So ESA is working in particular on a model of something like that. So I think, there's kind of the sky's not even the limit, I would like to say, especially given sufficient money and incentive the engineers can do. So I'm very optimistic. Was there a question over here in the back? Or I thought I saw a hand, sorry. No? Okay. Well, thank you all very much for coming. This is really fun for me.
Thank you.
And stay tuned, yeah.